Okay. Today I'm going to talk about two libraries I work on. One's named Thrust and the other one is named Cusp. Cusp is a sparse matrix library. Thrust is a sort of more general purpose algorithms library. And I think both of these may be useful to you, especially if you're just getting started out with GPU programming, because they make it a lot easier to use CUDA. Okay, so Thrust is a productivity-oriented library for CUDA. And what that means is that we are trying to make it possible to use CUDA with the least effort possible. So as little effort as possible getting to a satisfactory implementation of your application. Actually, can we dim the lights up here somehow? Sorry, I didn't realize how hard it would be to see. There, that's good. Thank you. Okay, so this is a complete program using Thrust. And so this is something that you would compile with in VCC as you've been doing before. And the way you get access to Thrust functionality is through header files. So everything in Thrust lives in a header file. There's nothing to link to. You just pull it in through that, and then you can use it within your code. So what this code does is it creates a host vector. So it's a dynamic array on the CPU memory with 32 million integers. It'll produce some random values and store that in this host vector using the generate method. It's going to copy that to the device using this device vector. So there's a host vector and a device vector, and they're pretty much equivalent, except one lives in CPU memory, one lives in GPU memory. And we can copy back and forth using just the equals between them. On the device now, in this dvec, we're going to sort the data, and I have a little note here about the performance that we get on the device. It's over 800 million keys per second, and that may not sound too impressive to you, but later I'll show you what you get on the CPU using the STL. And lastly, we can copy the results, the sorted results, back from the device to the host. So throughout the slides, I'll kind of explain, the different algorithms here and what exactly different parts do. But this is just to show you that with a very small amount of code, you can do something pretty powerful. Without this kind of library, it's very difficult to think about how you would, do all these things. You definitely need a lot of code just to move data back and forth to, initialize an array of data. So this makes it quite a bit more convenient, and it turns out you can implement very sophisticated things in much less time. Okay, so what we sought to do with Thrust is we want to make our CUDA programmers more productive. So you don't really get paid for writing lots and lots of boilerplate code, CUDA mem copies, CUDA mallocs. Those things are kind of error-prone, and no one really wants to do them more than necessary. So this abstracts a lot of that, and you end up making fewer mistakes and writing a lot less code. We want to encourage generic programming. If you're not familiar with sort of C++ and templates, I'll show you later what that means exactly. But the idea is that the algorithms that we have in Thrust, so things like sort, aren't particular to a particular, they're not specific to a particular data type. So sorting integers or sorting floating point numbers, you still call the same sort algorithm, and it figures out what kind of sorting it needs to apply. And the last thing is we want high performance. And later I'll show that even though we're doing this at a very high level, a very abstract interface, we can get very high performance because we can apply some cleverness to the way we carry out those computations. Okay, so Thrust, if you're familiar with C++, the best way to think of it is it's very similar to the C++ standard template library. So if you've used, std sort or, things like that in the STL, you'll be very comfortable with Thrust because it has a one-to-one analog for a lot of those algorithms. There are two major, the functionality comes in two major components. There are containers, and this is just the host and device vector that I showed you earlier. So containers can hold data, and then there are algorithms which act on data. And we have algorithms for things like sorting or reduction, scan, and so on. So to give you an example of what you can do with containers, in this case I'm creating a host vector. I'm going to store ints in it. And if you're not familiar with C++, this little part here just says what type we're going to put inside of it. So this is the way we tell C++ through the magic of templates that we're going to create a host vector with 2 elements in it, and we want to store integers. So if it was instead floats, we would put float in the little brackets there, and everything else could remain the same. So as before, we saw that we can copy from the host to the device just using equals. The opposite also works, so it's pretty convenient. And one really nice thing about this is that if you just want to set a few values on the device, so this array lives on the device, you can just use this kind of notation. You don't have to do a CUDA-mem copy of 4 bytes, to copy this integer over there. You don't have to do another CUDA-mem copy. It sort of happens behind the scenes. So this is pretty convenient because we'll often, compute something. Maybe we just want to read back a single value, maybe at the end of the array or something like that. And we can do that in a very convenient way. You can read back, like, here we're assigning values, here we're reading them back from the device, just using the brackets. So it's very, very convenient for that kind of thing. You don't want to use this a lot because every time you do, this kind of, this style, it does do a CUDA-mem copy. So if you're going to access lots of values, you should just copy the whole array over and then, iterate over them on the host. But if you just want a value or two, this is very convenient to do.
So it's just a new copy for a single value for 4 bytes in the case of Iterators, no more?
That's correct.
Okay.
But there's some overhead associated with that. So if you do a bunch, it can actually be quite slow. It makes more sense to do a batch operation then. Okay. One neat thing about this kind of interface is that we can make it compatible with the STL. So if your data is already in a list or a STL vector, you can just throw it right immediately into Thrust, and we accept that kind of thing. So at the top, I have a list in the STL. This is just a linked list data structure that C++ provides. I'm going to put 2 integers into it. And then if I want, so this may be something you have in an existing code that you've written long ago. If you want to copy that to the device, it's very straightforward. You don't have to do any real work. You just call the thrust copy algorithm and give it the beginning and end of your list, the beginning of your vector, and Thrust will perform the copy for you. There's a slightly more concise way of doing this using the constructor of the device vector. But really, they're both essentially the same. One thing to mention, if you're not an expert C++ programmer, is that to the left of all these different algorithms that I've shown in green, or containers, I have, thrust : or std : and those are called namespaces in C++. And what they're good for is sort of separating. Like if I have a sort algorithm in the STL, and I have a sort algorithm in Thrust, I need to have some way of distinguishing between them. And namespaces just give us ways of referring to them in an unambiguous way. So you can still call the STL sort on a host vector if you want. Thrust sort also works on that. And if you get tired of typing Thrust or std a bunch, and all you're using is Thrust, then you can use this kind of command, and then you don't have to say Thrust anymore. You'll just call the algorithm name. So it's very nice because you don't have to worry anymore about integrating 2 big libraries and worrying about name collisions. You just use the namespaces to control that. Okay, so you'll notice before, whenever I wanted to apply an algorithm to a vector, I did something like copy dvec.begin or dvec.end, and I passed those into the algorithm. What these are in C++ terminology is iterators. And what iterators are, they're essentially like pointers, and that's a perfectly reasonable way to think about them. They're sort of pointers that have a little bit more information associated with them that I'll talk about later. But you can treat them just like pointers. Anything you can do with a pointer, you can do with an iterator. So you can increment an iterator. You can dereference it with the star. You can treat it like it's a pointer, so you can use the bracket operator. So anything you can do with a pointer, you can do with an iterator. You can take the difference of 2 iterators to get the size of a range that they define. So it's very convenient, and you may say, well, why not just use pointers? And I'll explain why we talk about iterators as being something different in a little bit. As I mentioned, iterators, if you have a pair of them, that defines a range of elements. So here, before we were doing the beginning and end, and that just defined the range of that array or vector. You can also define a subarray. So here we have a vector of 10 elements, and we only want to sum the first half and the second half. And the way that we do that is we get an iterator pointing to the beginning of the array, and then we advance it by 5. So doing begin plus 5 gives us a pointer to the middle, and then we can sum the values in the first half of the array just by passing in begin, middle, and then we can get the sum of the second half by doing middle to end. So you don't just have to use begin and end. You can use any subsequence of that if you want also. A question is, what if I pass in the empty sequence? Usually an algorithm will have some default behavior for this kind of case. So this is an empty sequence. It'll just return 0 for us. The nice thing about iterators, and one thing you may have noticed about the examples I've given you so far, is that I never had to say where I wanted to run the algorithm. I just said use reduce or use sort. And the nice thing about this is that through the magic of C++, we can encode the data of where the memory lives into the iterator. So if I give you an iterator that I got from a host vector, I can later determine that that came and that lives on host memory. So I can call the CPU version of that algorithm. If instead it lives, if I obtained it from a device vector, I can later determine that, in the back end of thrust and call the CUDA version of that. So in this case, I can create, 100 integers on the host. I can, copy them to the device. And whether I want to reduce them on the host or device, I don't have to say reduce on the host or reduce on the device. I just call reduce, and thrust will figure out which version of that algorithm to call. So this is a nice technology, and this is why when we did a copy, we didn't have to say copy from the host to the device or copy from the device to the device. We just said copy, and it figured out which version of the copy algorithm it needed to apply. So this will save you a lot of errors. If you just have a bunch of pointers floating around in your code, then you'll sometimes make a mistake where you just forgot to copy it or you forgot to allocate something on the device or the host. But with this technology, the chance of that is diminished. So there are a lot of algorithms in Thrust. I won't talk about even half of them today. I think there's something like 50 or 100. And you can sort of classify them into a few different categories. There are algorithms for doing element-wise computation. So for each element in the range, apply some transformation. So compute f of x, sort, and y. There are a bunch of reductions. So the simplest one, reduce, will allow you to sum elements or compute the maximum, things like that. Inner product will do that, but for 2 vectors. So it'll do, the sort of mathematical inner product using 2 vectors. And then there are a bunch of others. Prefix sums, which I assume when they spoke about last week, are a case where you want to compute like the cumulative sum of an array. And sorting, of course, is a very useful thing to be able to do.
Some of those algorithms get the functions as parameters, something reduce and for each.
Yes.
Can you pass arbitrary functions?
Yes. We'll get to that in a second. But the question is, these are generic algorithms, so can we pass our own functors or functions to them?
Yeah, but there's some subset of, I don't think you can pass an arbitrary C++.
That's correct. It has to be a valid CUDA function. But I'll show the way that we can do that.
Are these algorithms included in a library?
Yes. So these, they're like 50 or more of them altogether, and we have documentation. So if you want to read about any particular one, I'll just point you at our website later. But yeah, these are all provided by the library. Okay, so just to give you, like before I showed you different algorithms like sort, where it took a single range of data and it sorted it. Copy, of course, has to take 2 ranges. So the way that we specify this, and it's a convention borrowed from the STL, is we provide the beginning and end of the first sequence, and then we just provide the beginning of the second sequence because we don't really need to know the end. We already know how long the input sequence is, So we don't need to know how long the output is. So it would be sort of redundant. So this is sort of the standard convention. If we have an operation like transform where it takes in 2 input sequences and 1 output sequence, again, we only use the beginning of the second and third sequence. So there's no need to specify b.end or c.end. I guess I misspelled it there. But because we already know how long A is. And this is the what was asked earlier. You can specify different functions here. This is a built-in one, plus. But I'll show later how you can specify your own. Okay, so there are lots of built-in functions that we commonly use. So if you want to add 2 vectors together and store it in a third array C, you can just use the built-in plus. And here I've omitted the thrust : just for brevity's sake, but in practice you might have that in front of everything that's shaded in green. So there's the different names are plus, minus, multiplies, there's divides, I think. A bunch of standard things. Anytime you have an operator in C or C++, there's one of these with a name associated with it. And the other interesting thing is that before we did, we just did reduce, and we ended it. We only passed in 2 parameters. Most algorithms in Thrust have some defaults. So the default reduction has an initial value of 0, and it uses the plus operation to reduce values. We can sort of specify a more customized operation by filling in these slots with our own choices. So if we want to compute the product of a bunch of numbers rather than the sum, we initialize the product to 1, and then use the multiplies operation to multiply the numbers together. So these are quite convenient, and I guess usually the default is exactly what we want. So when the most common reduction to do is just to sum numbers, so we use the default. But if you want to do something slightly different, often you can just use these built-in operations. Of course, you can do different types. So if you're doing integers or floats, you can still call reduce. It figures out what types to use inside the algorithm. So there's no need to write, like you can imagine, this is a big savings, because if you were to do this in just the CUDA C, you would have to write 1 reduction for integers, 1 for floats, 1 for doubles, and so on. And this is just not really a scalable approach. Okay, so now we'll get to customize things. So before we looked at cases where we would change some of the default arguments or use a built-in operator to change, the reduction from summing to taking the product of numbers. In this case, we can use customized types. So in this case, we're not using float, but we're using float2, so a pair of floating point numbers. And we can change the operation. So this transformation will take in a vector of 2-dimensional floating point numbers, so x and y in each structure. And it's just going to negate them. So it's going to take in a 2D floating point vector and then just reverse the x and y directions. And the way we do this, if you're not familiar with C++, this might look quite weird. So we're just passing in the beginning and end as usual. We're giving it the beginning of the output. So far this looks normal. But this is the thing that we're adding new this time. And this is called a function object, or functor, in C++. And I've written it up there. So the way to think of this is that we're just passing in a function that we want to apply to each element of the input. So inside thrust, it's going to loop. It's going to use like a CUDA kernel to loop over all the elements. And it's going to apply this function written inside a class. So it may take a little getting used to. This is kind of an odd way of writing down a computation. But the benefit of it is that all you have to write in order to do a new algorithm is that little bit of code. You don't have to write a CUDA kernel. You don't have to make sure you get all your bounds right and stuff like that. You just write that small bit of code at the top and feed it into the thrust algorithm, and it takes care of absolutely everything else for you. So we'll do some examples like this in the lab. But I just wanted to show you this because it sort of explains how you can get more customized functionality out of these generic algorithms. Okay. So, sorting, before we were sorting integers or floats or something like that, so it was pretty obvious what we need to do. We were just going to sort in ascending order using the standard comparison. But sometimes you might want to sort something that doesn't have an obvious way of sorting it, or you want to override the way that you would normally sort that. So the way you do that in Thrust is you call sort as usual at the beginning and end. And then you can pass in a comparison object here that works just like the functor we saw on the previous slide. So in this case, I'm giving the sort algorithm a functor that tells it how to compare two objects. So it's just if you've used qsort before in the C library, it's basically the same idea. I tell it how to compare two float 2s. So I'm just going to, in this case, I'm just going to sort float 2s based on their x component. I'm going to ignore their y component. And this will give me, after I call this sort algorithm in Thrust, an array of the float 2s that are sorted by their x component. I could change this if I wanted to. I could sort based on y or some combination of x and y. Or if this is your structure, there might be a dozen different things you might want to consider when sorting numbers. But the nice thing is you don't have to write sort, you just have to write the comparison method. So it may be a little strange and an awkward way of expressing the computation, but I assure you it's much easier than writing your own sorting algorithm for a particular case.
If I want to use a mathematical function, should I wrap the CUDA function with a function?
So what kind of mathematical function are you?
Design?
Oh, okay. So the restrictions, so to get back to your earlier question, the restriction is that whatever you can put in a host device function, you can feed in here. So if there is a CUDA version of that mathematical function, you can use it. But that's the restriction. So in here, you can kind of ignore the struct thing. That's sort of an artifact. If you can make sense of this internal thing, make a host device function that computes the thing or does the comparison, then you can use it within Thrust. The limitation is you can't call things in the standard library, like you can't call strcomp from the C library, which is kind of annoying because you end up writing your own versions of those sometimes. But for simple things like this or basic mathematical operations, there's usually a CUDA version of it available already. Yes?
Does the compiler actually optimize and enhance or inline all that,
Yes.
that stuff?
So the question is, does the compiler optimize and inline stuff like this? And the answer is yes. And actually, on all the hardware before Fermi, it was forced to inline things because it didn't support function calls. On Fermi, it will inline lots of things. Like this is such a simple thing, it will definitely inline it. And in practice, we've never seen a case where the performance greatly differed from what we would expect from an optimized implementation. So whether you wrote these kinds of things by hand or used the Thrust version, in every case we've sort of measured, we've seen agreement between those two. And if you want to force it to inline, there's a compiler directive for that. Yep. Okay, so here's a slightly more sophisticated functor. And the difference between this one and some that we looked at before is that this one has some state in it. And this is a useful thing. So before we had, something to compare to floats, float 2s. So we didn't need any other state, or we had some transformation of the float 2. So it's just a pure function. It just took an input, and we knew how to compute the output. In this case, we want to count numbers. In this case, we want to count all the integers that are greater than 10. But we want to do it in a way that we can change this threshold. And the way we can do this with C++ is we add an integer to this structure. So this is where we're going to place our 10. So we have to create a constructor. So if you're not familiar with C++, sort of ignore this part. But the idea is that rather than just taking an input, we can also put some other things inside the structure that we're going to use to compute the value we want. So if we wanted to count all the numbers that were greater than 20, all we would have to do is change the threshold inside this structure and pass that predicate into the algorithm. Question? Oh, well, the question is, how does Thrust know to copy this from the host to device? Well, this is just a structure, so it will copy, CUDA knows enough to copy that when you pass it to a global function. So if you create a struct and put a bunch of different things inside and pass that to a global function, CUDA will handle that much for you. What it won't handle, if you put an array inside this with a pointer, it will not handle that for you. So there are some caveats associated with it. But for things like this where you just want to put an integer or a small array with fixed size, it works, as you'd expect. So it's a good question. So one thing you might want to do if you're interfacing a thrust code with an existing code or vice versa is you sometimes say, Nathan, I've written, I have some existing kernels that take pointers to arrays. I don't want to use iterators. I don't want to use these containers or vectors or anything. Can I still use thrust? And the answer is yes. So in this case, I have a device vector. So I create a device vector with 4 integers. And what I'm going to do is I'm going to take a pointer. I'm going to get a pointer to the beginning of that device vector, and then I can pass that into a CUDA kernel. So it's, after we get a pointer here, this is just normal CUDA code as you've written so far. I can use this pointer however I want and treat it exactly like a pointer if I had allocated it with CUDA malloc. And you can do the opposite also, which is probably more useful. So if you've already allocated some memory using CUDA malloc and you have a pointer to it and you want to pass that into a thrust algorithm, remember before, if I just have a pointer, I don't know where it lives. It could be a host pointer, it could be a device pointer, it could be anywhere. So the way we sort of tell thrust where that pointer points is to wrap it. So if it's a device pointer, we wrap it in this device PTR structure, and then we can pass it into thrust algorithms just like we did before. So it's a way of taking data that you've already allocated or you manage yourself and interfacing it with thrust, and passing it into algorithms and so on. Okay, so to summarize what we've looked at so far, we had containers, so we had host vector and device vector. Those were nice because they managed memory for us. Another thing about vectors that I didn't mention is that if you declare and allocate a vector inside a function, and then you return from that function, it automatically cleans up the memory for you. So if you forget, common error is to forget to do a CUDA free or a free in C. That's not an issue with vectors because they automatically release their data when they go out of scope. We looked at iterators. A pair of iterators defines a range, and this is how we specify what data we want to act on. And algorithms are general in that they support different types, so we didn't have special reductions for floats and so on, and operators. So you can easily change the kind of algorithm, the particulars of the algorithm using function objects.
2 questions. So you can you use every class that have an iterators implemented on the device, or you have to set the device property? Because you put device vector, for example.
Yes.
Not a vector, a simple vector.
Okay, that's right. So the question is, what can I use these, apply these algorithms to? And you can apply it to the STL containers, so
Yes.
things that have a begin and end. The only thing that will actually run on the device now is things obtained from a device vector. In the future, we could add a device map or something like that, or device list. But for now, it's just device vector. But yeah, the idea would be anything that has an iterator interface, we would want to make it compatible with this.
What can you say about memory coalescing and iterators?
Okay, so the question is, what about memory coalescing? So for all these cases I've shown so far, the algorithm will just do kind of what you expect. Like if I'm doing, let me get a better example. So this transform. The way we wrote the algorithms, like transform, does what you would expect. It uses threads and it sort of assigns them in a standard fashion. So if you're, because the device vector is aligned and the way that we access memory is just as you'd expect, it's completely coalesced. If you give us a device vector and then you take an offset using an iterator offset or something, you'll get unaligned access to that unless for some cases we've actually optimized that so it will make aligned access even if you give us unaligned data. But for the most part, if you do some unaligned thing, it'll be unaligned. But I think everything is coalesced unless there's some reason it can't be. Okay, so we have another set of slides called Thrust by Example that goes through some more sophisticated uses. It also sort of encourages you to use these best practices that are described there. So these are ways of getting more performance out of thrust. And the performance advantage is not something like 10 or 15 or 30%. It's often like 2x or 3x because you're really reducing the amount of memory bandwidth you use. So I would encourage you to look at those slides. They're available on our website. And at the top, I have leverage generic algorithms. What I mean by this is that when you come to an algorithm, and you have sort of often two ways of doing it. You can either apply a very general strategy to it that may be a little wasteful. So if you want to compute a histogram of data, one technique is sort of to sort the data and then sort of compact it. And that's an example in this other pair of slides. An alternative would be to do something very specific. Write custom kernels just to do that one particular thing. And there's a trade-off. Sometimes the customized thing can be faster. It's going to take you longer to write. On the other hand, you can use this more general approach, but it might be a little expensive. And you might wonder, well, which one is better? This will save me time, but I may want the performance of this. And what we hope to obtain with Thrust is a way of saying, no, use this almost all the time because we've written a very highly optimized implementation. And to give you an example of that, we have the sort algorithm in Thrust. And if you're sorting things like characters, shorts, floats, or ints and doubles, if you're thinking about this like CPU sorting, it's sort of misleading because what our sorting algorithm can do is much, much faster. Like for characters and ints, it's 20 or 30 times faster. So rather than trying to be clever, like if you can reduce your algorithm to sort plus some other something, just do that first. Don't try to be clever first. Because what we can do inside our sort algorithm is apply a lot of very sophisticated techniques. So in this case, we're using a radix sort to do these kinds of sorting operations. And it turns out to be much, much faster than what you can do on the CPU. It also turns out to be much, much faster than a lot of customized things. And actually, the sorting algorithm we use that I showed the performance on the previous slide was actually on Slashdot a few months ago. So it, I think, is still the fastest sorting on any processor. Okay, so if you want to learn more about Thrust, we have a page on Google Code. There are a lot of examples, nice tutorial. We'll use some Thrust things in the lab today. But if you're interested in knowing more, there's a lot of resources here. And we even have a mailing list if you have a question you want to ask. Okay, so that's the first half of my talk. Second half, I'll talk about Cusp, which is a library for doing sparse matrix operations. And actually, Cusp uses Thrust for about 90% of its functionality under the hood. So again, I'll show you a complete Thrust program, or Cusp program. And in this case, we are solving a linear system. So the way this works, again, we pull in all the functionality using from header files. We're going to create a matrix. So this is the hybrid format that I mentioned earlier in the week. We're going to create one of these. We're going to read in a matrix from the disk. So this is a sparse matrix stored in a file, in a standard file format. We're going to create some, X and B vectors. In this case, we're just going to fill the X vector with zeros. We're going to fill the B vector with ones. So this is not a very interesting linear system to solve, but it still illustrates what to do. And lastly, we're going to call the conjugate gradient method to solve this linear system. So this is all you have to do to get some basic functionality up and running. And it's sort of consistent with the Thrust idea of doing things very concisely and doing a lot of work automatically. So these arrays here are just like the device vectors. So the way that we specify it is a little different. Rather than device array 1B, we put the device in this slot here. but otherwise it's essentially the same. Okay, so I'll just go over the major features of Cusp. It has a lot of different matrix formats, so all the ones that I described earlier are in there, so you don't really have to worry about them. The dense containers, okay, so we have, as I mentioned, these 1D arrays. They act just like the thrust vectors I showed in the previous slides, so you can set the elements if you want. They work just like you'd expect. There's also a 2D structure. So in this case, we can create a matrix, a 4x3 matrix, fill it with zeros, and then set the elements just using this sort of notation. So it's a pretty convenient interface to that. We can also switch it. So by default, if you declare a 2D array, it'll give you one with row major ordering. You can change it to column major just by specifying an optional parameter here. So the sparse containers are probably the more interesting part. You can set the values within the container. So in this case, recall that the coordinate format had 3 different arrays, one for the row indices, the column indices, and the values. And we can fill out a matrix this way if we want. You can do this in host code, and it's pretty efficient, and then transfer it to the device. The other formats are all very similar. You can set the entries exactly like this. Probably the most appealing part of this package is that Cusp will do the format conversions for you. So if you start with a coordinate format, fill out the entries yourself, you can convert that to a CSR format just in a single line. So this will do a conversion from the COO matrix up here to the CSR format here, and it'll actually automatically transfer it to the device at the same time. So you can convert between any 2 formats automatically. In this case, we did a host to device copy and a conversion at the same time. So it'll convert on the host and then copy to the device. There are actually device versions of all these conversion routines too, which are quite a bit faster. So basically, you don't really have to know too much about the implementation. Just know that if you have a matrix, it's often easier to start with a coordinate matrix or a CSR matrix, but to do the computation, you may want to convert to LPAC or something like that. I guess that should be ELL, right? You can just do it with 1 line of code. As I showed before, we have support for file I/O. The only format we support now is this matrix market file, which is pretty simple. You can actually look at this. It's just a basic text file. But it's a nice way of storing matrices. You can get these examples online. There's big repositories for them. So it's pretty convenient format to use. And you can read and write it. So if you want to get data out of thrust, the most convenient way is to write a matrix market file. There are lots of algorithms. So before I showed you the conjugate gradient iteration, that's one algorithm. Another one is multiply. So in this case, we can do a sparse matrix vector multiply. So we do y equals 8 times x. And you can feed in other things, like you can do sparse matrix times sparse matrix, store that in another matrix. Do I have that here? Okay. So the nice thing about it is it works for any kind of multiply that makes sense. So it's going to do, this can be a dense matrix, and a dense matrix, sparse matrix, sparse matrix, sparse matrix. And it will decide what algorithm to do. So you just say multiply, and you don't have to tell it what format or anything. It figures that out for you. Different algorithms. We have a bunch of BLAS algorithms that we've written ourselves to do basic things like compute norms of vectors, do AX plus Y, stuff like that. The reason we did this is just to make Cusp self-contained. So you don't need the CUDA BLAS library. You can just use this as a standalone.
So that class functions are actually implemented with Rust.
That's right.
So you are not using at all.
That's right.
Rust library. And I think you get almost the same performance from
That's
this
right.
implementation that from the Q plus one, right?
Yep. And the reason is it's not hard to implement them. Like you don't have to be all that clever. So that's definitely true. So we have a few other algorithms. You can transpose a matrix, even a sparse matrix, which is nice to have. The only graph algorithm we have now computes a maximal independent set. We're also thinking of doing graph coloring and stuff like that, and graph partitioning in the future. Solvers, I showed you before the CG solver. This is just another example. One nice thing that you can do with this kind of interface is, so before here I just did CG and I gave it the matrix, the current approximate solution X, and the right-hand side B. But sometimes you want a little bit more information out of your solver. So what you can do, in the top here we sort of override the default convergence criteria. So by default, the solver will run a given number of iterations and stop at a certain tolerance. But if you want to make your own choices for those, so if we wanted to iterate at most 100 times and stop when we get to this residual tolerance, then we can change those parameters as we wish. Another nice thing about this interface is that we can make, so these monitors allow us to print information and stuff like that if we want to. So by default, the monitor just tells us when to stop, and it monitors the convergence of the algorithm. But you can also make it print something or do something like that at each iteration. So in this case, I'm using the verbose monitor that I set up down here. And what that does is it just prints out the residual norm at each iteration. So you can do whatever you want. You can write your own monitors and change the behavior of the solver a little bit through this interface. Cusp has a few preconditioners. The one that I'm working on the most lately is this smooth aggregation multi-grid preconditioner. And the way you throw that in, I'll talk about more about preconditioners tomorrow, but the way you pass that in is just by adding a fifth argument to the solver. The purpose of a preconditioner is that it just accelerates the basic solver. So using this kind of preconditioner with conjugate gradient iteration can often save you, a great deal of iterations. So rather than converging in thousands of iterations, maybe it only takes 10 or 20. Okay, and the last feature of Cusp is views. The nice thing about views, so before we had things like device vector or host vector, we had CSR matrix and stuff like that. Those things all allocate their own memory, and if you want to get data into one of those, you have to actually copy it. So it's kind of annoying because copying is expensive. It forces us to duplicate our data. A nice feature would be to just, if we had existing data, so if we already had a CSR matrix on the device that we allocated ourselves, and we wanted to solve a linear system, we'd like to wrap that, very cheaply, no copies, and that's what views allow you to do. So there are examples of this on our website. It's a bit complicated to use, but it's a very nice feature. So like Thrust, we have a Cusp website on Google Code. You can just Google for Cusp, and I think it comes up on the front page. So it's pretty easy to find. And that concludes my talk, so thank you. Sorry. Are there any more questions before the break?
So are both libraries implemented with the header files?
Yep, they're pure template libraries. So we've actually, so in the future we may add a runtime to implement some feature, but it's just so much easier to distribute header files versus a compiled library that we've sort of stuck to that for now. So yeah, it's very easy. All you have to do to get these libraries is download them and then copy them to your include directory, and they're already there. So okay, well, I'll see you all at the break then.